All right, welcome to lecture 19. All right, this lecture, like most of them, gonna have three parts. Part A, B, C, so you gotta watch them all right? So if you're tired of talking about moles, if you're tired about balancing reactions, if you're tired about doing math, good news, we're not doing that in this lecture. All right, so we're gonna move on and talk a little bit more about details about atoms and how atoms are put together. So let's go ahead and get started with part A. All right, so earlier in the semester, like as in a few weeks ago, right, we talked about the structure of an atom. So we're going to get into more details about that in this chapter. So specifically, let me just remind you, we talked about the atom really has two regions. It's got the middle part, that's the nucleus. The nucleus is where your protons and your neutrons live. And then there's this sort of outer area, and this outer area is where the electrons are. Now, this outer area is like a lot less dense, and sometimes you're going to hear it referred to as being called the electron cloud. And really what we're going to focus in on is there any organization to this electron cloud? Is there any like specific way the electrons are put together out there, or they're somehow organized in some way? So, well, let me just give you the bottom line answer. Is there any organization to this outer area? The answer to that question is yes. So really, we're going to be learning about how it's organized. And the reason we care about this is because it turns out the way that the electrons are organized in the atom, in the outer part of the atom, is going to have a lot to do with the way an atom is going to behave. It's going to help us understand why are some atoms really reactive and other atoms aren't reactive. So it's going to help us understand that. All right, so that's the ultimate goal of this chapter. Now, before we get into that, turns out we need to kind of talk a little bit about light. And why are we talking about light? Well, the reason is because the first clues to how this electron cloud is organized came from experiments involving light. So before I can tell you about the electron cloud, I got to tell you about light. So that's what we're going to start off with. All right, so let me go ahead and flip over to the next slide and we'll start and we'll spend actually this entire part of the lecture learning about light, this first part. Okay, so one thing that's important to know about light is that when you look at a normal, regular, like white light bulb, like maybe in your house or whatever, when you have some sort of light bulb and it's giving off white light actually contains all the colors of the rainbow. So if you use some sort of prism or there's other devices, you can separate that light. And when you separate it, you'll get all the colors of the rainbow. So white light from like a light bulb is actually emitting red, orange, yellow, green, blue, indigo, violet, right? Like Roy G. Biv. Maybe you've heard of that before. It's emitting every single color of the rainbow. Now, it turns out there's other things that emit light that don't give off every single color of the rainbow. And specifically, the one that we're going to talk about is just how like you can run electricity through a light bulb and it gives off light. You can run electricity through elements and they also give off light. Now, this diagram shows you like this is a tube full of mercury right here. Mercury is Hg, and it's mercury gas. They've turned it into a gas. So when you run electricity through it, it looks blue to your naked eye. All right, so it looks blue. Now, the other one is hydrogen. When you run electricity through a tube full of hydrogen, just like a light bulb, it gives off light, and it looks pink to your naked eye. So that's hydrogen right there. I guess it's H2, isn't it? Now, when we look at these colors a little more carefully, just like we talked about a minute ago, how a light bulb, it looks white to your eye, but it's actually giving off every single color. These elements, they might look blue and pink to our eye, but they actually are giving off more than one color. So let me show you a diagram. Like if we could separate the colors away from each other, what would we see for these samples of these elements? So what we would see is that hydrogen is actually giving off three colors. it actually is giving off, and this is going to be a little hard to note to you, it's giving off red, it's giving off kind of like a teal, and it's giving off sort of like a purple, actually two shades of purple. So hydrogen is giving off three kinds of light actually when you run electricity through it. Red light, kind of a bluish teal, and like a purple. Now, if we look at other elements and we do the same thing, we'll see that they are giving off different colors of light. Helium is giving off red light, and when you run electricity or heat through it, and yellow, and then also some blues. All right, so remember, when we look at a light bulb, we see every color. But when we look at an element and it's glowing, because maybe electricity is going through it, we only see a few colors. So why is that? Why is it that we're getting only a few colors? And why is it that every element gives off a different set of colors? Well, this is kind of going to lead us into understanding electrons. So let me write a few notes about this. All right, so first off, the questions that I am curious about is, first off, why is it, let me switch colors here. Why do elements, when you run electricity through them, or heat actually, produce, we'll say, only certain colors of light? Like red and blue, maybe, like we saw for hydrogen, wasn't it? And the other question I'm curious about is, why do different elements produce different colors? Different elements produce different colors. How do different elements produce different, I guess we'll say, colors of light? All right. So that's what we're going to focus in on first. Ultimately, again, it turns out the answer to these questions has something to do with electrons. So we're getting to that, I promise. All right. A couple little terms, too, though, that we should start with. When light contains every color of the rainbow, like you saw with the light bulb example, when light has every single color of the rainbow in it, like a normal light bulb, that's called a continuous spectrum. A continuous spectrum. You see every color. And then when I showed you that diagram of like what is happening with hydrogen or helium, or I think neon was on there too. I didn't really talk about it though. And you only see certain colors of light. That's called a line spectrum. So elements give off only certain colors. They give off what's called a line spectrum. So only certain lines, only certain colors from the rainbow. All right, so with that little introduction, let's get into some details about light. All right, so let me flip over and we're going to get into it right now. Okay, as we kind of continue on our little introduction to light, let me tell you, light, it turns out light is made up of waves, all right? So light is made up of waves. So, you know, a wave, kind of like an ocean wave, all right? So whenever we describe a wave, it could be light waves, it could be sound waves, it could be ocean waves. We describe waves using two terms. So term number one, a little more vocabulary, is the term wavelength. Wavelength is just the distance between two peaks of a wave. So how far is it from here to here? What's that distance? So if we could measure it, how far apart are those peaks? So just like everything in chemistry, yeah, there's units. And since we're measuring a distance, if we were measuring a distance, we could use something like, I might tell you how far apart those waves are in like meters, or it could be like feet. How many feet apart are those peaks of the wave? Typically, they're going to be pretty close. When we talk about light, the peaks are pretty close. So I might, instead of using like meters or feet, I might use a unit like, I don't know, millimeters, or even like nanometers, something like that, like a small unit. Now, just like there's always a unit, oh, in chemistry we love symbols. So the symbol for wavelength is a Greek letter. It looks like an upside down Y. It's called lambda. Lambda. Oh, lambda. Ugh, I think I spelled that right. Lambda? I don't know. Whatever. Lambda. I don't know. I'll look it up. I'll let you know. Is there an M in there? All right, lambda. It's a Greek letter. Well, it looks like an upside down Y. All right, so this distance is lambda. So that's that upside down Y right there. All right, so there's another way we can describe waves. And that way, the other way is something called frequency. So frequency is the number of peaks of a wave that pass per second. So to understand frequency, you have to imagine, just like waves on the ocean, they're not standing still. Light waves are also traveling. So if you were to sit here, and let's imagine this wave is kind of coming towards you, and there'll be a bunch of waves, right? This wave is not just it's gonna have a bunch of peaks. And you were sitting there and you count how many peaks pass me in a second as the wave comes in towards me. That's what frequency is. How many peaks pass me in a second? All right, so there's a symbol. The symbol for frequency is also a Greek letter. It is the letter nu. All right, that one I know how to spell, N-U. All right, it looks like a V with some lines on the end. All right, so frequency, the symbol is nu. Oh, I should have put that down here, shouldn't I? Well, I'm messing all up. Oh, well, that's okay. One other thing I wanted to tell you is the units, though. And the units on frequency are usually there might be called like 1/seconds, like peaks per second. There's another name for that, which is hertz. So you might hear about this if you've ever had to deal with anything like electrical in your house. Like the electricity in your house, the way they send it to you, it's actually a wave as well. And for the electricity in your house, it's 60 hertz. So what does that mean? It means that there's 60 peaks coming out of the wall every second. 60 hertz is the frequency of electricity in your house, for example. All right, with that, let's get into just a few more details about light in this lecture. All right, wavelength, how far apart are waves? Frequency, how many waves pass you per second? All right, let's move on. All right, so while I was flipping over, I checked lambda. How do you spell lambda? Lambda, it just doesn't look right, but it's the way I spelled it originally. All right, that's how you spell lambda. All right, like if you have to write it out. Usually we'll just use a symbol. All right, let's move on. All right, L-A-M-B-D-A. Okay, so what we're going to do is we're going to talk about how different waves compare. So could be light waves, could be ocean waves, could be sound waves. So in this case, what I've drawn up here is a couple of waves. We're going to call them wave A and wave B. Now, to see if these terms that we're going over right now make sense, let's look at comparing these waves. So first off, I want to think about which wave has a longer wavelength. So it could be wave A or wave B. Longer wavelength. So what is wavelength again? Wavelength is how far is it from here to here? How far is it from one peak to the next? Now, if you just look at it, and I'm not going to bother to get out a ruler or anything and measure it, I can just sort of tell with my naked eye. In wave A has a longer wavelength. The waves are further apart. So I guess wave B would have a shorter wavelength, wouldn't it? All right. Now, there was that other term we looked at, frequency. So which one has a higher frequency? All right, which one has a higher frequency? Now, for that, again, you have to sort of imagine they're traveling. Which way they're traveling doesn't really matter. So you're going to sit here and count how many peaks pass you. And we're also sort of imagining they're traveling at the same speed, right? So if you were to sit there and count, and I want to ask a higher frequency, which one are the peaks coming at you more quicker? That should be, they're coming at you quicker in wave B. So in wave B, they have a higher frequency. a higher frequency. So because they're closer together, they're going to pass you more often. They're going to come quicker at you because they're not so spread out. So wave A would have a lower frequency. Now, the last question on here, I haven't actually talked about. Which one has more energy? So one thing that we're going to see is different kinds of light carry different amounts of energy. So the way that it works is when the peaks are close together, that is going to be a kind of light that has a lot of energy. So the last wave B, would actually be high energy. They're close together. When they're more spread out and they're kind of more gentle, that would be low energy. All right. So I want to mention all what I've just written up here always goes together. High energy light has a high frequency and a short wavelength. The peaks are close together. Low energy light, the peaks are further spread out, and that goes along with a lower frequency. All right, so with that, a few more things about light. Let's talk a little bit more about light. All right, so we've talked about how they're made up of waves. Now, it turns out when we look at light, there's actually more than one kind of light. And the different kinds of light, the way that they're different is they're differing in the amount of energy that they're carrying, okay? So some kinds of light carry a lot of energy. So what does that mean as far as the way they look? It also means that high energy light, the peaks, there we go, the peaks are close together, and a low energy light, the peaks are more spread out. All right, so all kinds of light. So they're listed here. There's 7 of them. They're not in order. I'm going to talk about them and put them in order. I want to go from the highest energy kind of light to the lowest energy kind of light. So one way to think about high energy light, it's the most dangerous kind of light. So you see we got visible light, radio waves, ultraviolet light, infrared light, X-rays, gamma rays, microwaves. One of those is super dangerous. The one that is the most dangerous is gamma rays. Gamma rays are the most dangerous kind of light. In fact, sometimes gamma rays, they can be released from exploding stars. And if that was to happen near us in the universe, it could actually wipe out all the living things on the planet if we had this gamma ray, like, come towards us. So that's a way that the world could end, is gamma rays destroying everything on Earth. Uh-oh, that doesn't sound very good, does it? Gamma rays are very dangerous. So luckily, they're not very common either. They can come from exploding stars, though. All right, other kinds of dangerous light. High energy light. Well, if you look at that list, does anything else look a little dangerous on that list? X-rays. X-rays. Hey, if you go to the doctor, yeah, you get your X-ray. They don't stand next to you, right? They stand way off in the corner because they don't want to get the X-rays and stand there all day and be exposed to X-rays. So, and they put, maybe some lead shield over you to protect you a little bit. So X-rays, also super high energy, also kind of dangerous. All right. What else on this list looks kind of dangerous? Do you have any ideas? Think about it for a minute. Ultraviolet is the next. Ultraviolet is the one that gives you skin cancer. So still potentially dangerous, not quite as dangerous as X-rays, but it's still kind of dangerous. Ultraviolet is next. All right, as we keep on going down the list, the next one is actually the kind of light we see. So the kind of light we see is visible light. It's a little bit lower in energy. If we keep on going down the list, the next highest energy kind of light, a little lower in energy, is actually infrared light. Infrared, you might have seen it, you can buy infrared cameras. People give off infrared light. It's basically heat. Heat looks like infrared light if you have the right equipment. And then, a little lower in energy than that. Sometimes people are surprised by this. Microwaves are actually pretty low in energy. Yeah, you cook with them. They're also what's used in your cell phone. They use microwaves. So, if you're near your cell phone 24 hours a day, there is a chance it could be dangerous, but definitely not as dangerous as sitting in the sun all day, which is like, what did I say, ultraviolet light, right? All right, and then finally, the lowest energy is radio waves. All right, so if we put that all together, when we kind of think about all the different kinds of light and rank them from high energy to low energy, this is what you come up with. All right, so this ranks light from high energy to low energy. So again, high energy is when the peaks are close together. And on this diagram, that is the far right side of this diagram. See how close those peaks are? That's high energy light. And just like I talked about, oh, that's gamma rays. When they spread out just a bit more, we get to X-rays. When they spread out a bit more, those peaks, we get to ultraviolet. And then we get to visible. I'm going to talk more about visible in a minute. And then we get to, if they spread out a bit more, we get to infrared. If they spread out a bit more, you get to microwaves. And then the lowest is radio waves. And that's when the peaks are really far apart. All right, so the one part I want to spend just a little bit more time on is visible light. All right, because that's kind of what we started with, right? Visible light, there's different kinds of visible light, like the rainbow. Now, when we look at visible light, it turns out not all kind of visible light has the same amount of energy. So just like gamma rays have a different amount of energy than X-rays, when we look at the colors of light, different colors of light have different amounts of energy. And it's kind of broken down at the bottom there, but it's in the same order that you see a little higher up. The left side of this diagram, this is low energy. Red light is the lowest kind of visible light, the lowest energy kind of visible light. When we move to the right, we're getting higher and higher energy. So the highest kind of energy of visible light is violet light. And everything else is in between. So red is the lowest, and then you go orange, and then you go yellow, and then green, all that Roy G. Biv business. When you get to the far right-hand side, violet is the highest energy. So in violet light, the peaks are a little closer together. In red light, they're a little further spread out. Now, one other thing I want to point out to you on this diagram is if you have a little bit more energy than violet light, you're a little better than violet light. You're a little better than violet. We call you ultraviolet. So ultraviolet is slightly more energy than violet light. Now, it kind of works the same way on the other end. Red light is low energy. But what if you have a little less energy than red light? You're inferior to red. You're less than red. You're infrared. So those kinds of light are kind of, their names kind of go with the colors on the rainbow, actually. All right, so different kinds of light, different amounts of energy. All right, with that, let's see if this is making sense. Let's talk just a bit more, and maybe we'll do a few practice questions. Man, we haven't done any yet. That's not too good, huh? Okay, so you can see that this chapter is a little different, right? There's not a bunch of math and stuff. It's mostly a bunch of terminology. So you got to keep these terms straight in your head. Let's see if they're making sense so far. All right, so a little practice question. Which one of these waves has the highest frequency? The highest frequency. Oh, be careful with that word. The highest frequency. Red light. This is kind of what it looks like, the waves. You can see them. And then green light or blue light. So by the way, the numbers they're giving you, that might help you out a little bit. Let me just explain them to you, though. So that's the wavelength. So that's the distance from here to here is, for example, 600 nanometers in red light. While down here, the distance is 540 nanometers in green light. And down here, the distance is 450 nanometers. All right, I want to give you a little hint, though. I ain't asking you about wavelength. I'm asking you about frequency. Which one has the highest frequency? Oh, it should be C. So blue light has the highest frequency. Why? Because if you're standing here and these fellas are coming towards you, the one that's going to come, the peaks are going to be the most frequent to pass you would be in C. So I'm not asking you about the distance. I'm asking you if when they come by, which wave would the most peaks pass you in a second? So it should be C, highest frequency. All right, let's do another one. Let's do another practice question. Another one. Let's make sure these terms are making sense. I hope. Okay, another little review question. So different kinds of light, they have different amounts of energy. All right, so this question says, rank these fellas, list them in order of increasing energy. So there's 4 options, I guess. I want you to find the one where you go from low energy to high energy. So which list gives you the lowest energy to the highest energy? Not all kinds of light are there, but on the list, which one goes from low energy to high energy? Okay, one more practice question. All right, so we've been talking about these 2 terms, frequency and wavelength, right? Frequency and wavelength. So this one asks you, how are they related? So there's 3 choices, A, B, and C. One of them's right. Okay, so that's pretty much it for this lecture on light. Oh, we know all we need to know about light. So in the next section, we're going to be learning about, well, how does this have anything to do with electrons? We're about to get into it. If you're confused on this, let me know. I'll help you out. And otherwise, we're going to move on to electrons in the next section.